Good morning, children. Today we will talk about effect of dielectric on capacitance of capacitor. Yesterday we talked about capacitor, how it works and how many types of capacitor can we have. As I told you that can have a parallel plate capacitor, a cylindrical capacitor and a spherical capacitor. The principle of working is same. But in our syllabus, we'll be only talking about parallel plate capacitor in detail. What did we do yesterday? Yesterday we talked about capacitance of a parallel plate capacitor, and the expression which we obtained came out to be C is equals to epsilon naught A upon D, where D is the distance between the plates of the capacitor. A is the area of these plates. This I have here made in terms of a line only, but it is a surface. So A is the area of the surface. Epsilon naught, already you know that it is a constant. So as epsilon naught, you already know it is a constant. Now I told you that if in case this whole space is filled with some dielectric, means initially what we have talked about here is, in this case this expression has been derived considering that there is air between the plates of a capacitor. If instead of air there is some other insulator which is having some other value of dielectric constant, then in that case your C will come out to be K epsilon naught A divided by D. That means if I take it as say C dash, then in that case C dash will be equal to K C. Capacitance will become K times the original capacitance. Now what we are going to do is, we'll place a dielectric of a given thickness. That is, the whole space is not filled with dielectric, is only a part of it of thickness say T, which is filled with a dielectric constant say K. So now the situation is, we are having a parallel plate capacitor of plate area of cross section A, distance between the two plates as D, charge density on each plate plus sigma and minus sigma, potential difference created between the two plates as V, and as you know, because of plus charge density here and minus charge density here, an electric field will be set up in the direction from positive plate to negative plate. Let us take this as E naught. This is the situation. Now if the whole area would have been filled with K, my value would have come out to be KC, the original value. But what if it is only a part of it is kept here? Now first we'll see how a dielectric will behave when it is inside here, kept between an electric field. I'll take it here only. See, this is made up of atoms. Dielectric means an insulator. So what is the specialty of insulators? The outermost orbit electrons will not come out from the atom. They will not be free to move. So let us consider a few atoms. Say atoms will be spherical in shape. Now when we are putting this dielectric in electric field of this capacitor, then what will happen? These atoms will not remain spherical in shape. They will start changing their shape as this. I'll take it a little bit broader so that I can at least make 3 atoms together. And what will happen? Negative charges will be towards this side and positive towards this side in this manner. I'll show you in a bigger space. See, this is the dielectric. Electric field positive here and negative here. So, atoms will take this shape with minus here and plus, but will not come out of the atom. Atom will now start getting oval shape with polarity like this. And how much they will be polarized will depend upon the strength of the electric field between these two plates. That how much charge is being stored by that capacitor or how much charge is there on the plates of the capacitor. If the charge is more, they will get more polarized because the effect of electric field will be more. If it is less, they will be less polarized. And what if keep on increasing the electric field or the charge on the capacitor? A limit will come when after becoming spherical and oval in shape, they will break down into free electrons. That much electric field which a dielectric can withstand without its breakdown is known as dielectric strength of that material. That is, at that point when its dielectric strength will be reached, the atoms will break and the electrons will become free to move, and now it will not behave as an insulator. So what we have to keep in mind that we are working here, we assume that we are working it here. The electric field is such that it is not going to break down, but that is known as dielectric strength. So in this way you can see that the atoms will get polarized to a certain extent and they will arrange themselves like this. And now see, I'll draw a dotted line here taking one charge on one side. Now see, this is a negative charge, this is a positive charge. These are in pair, see, plus minus, plus minus, plus minus, plus minus. These are going to cancel each other. This is throughout the slab. And a net negative charge is here and a net positive charge is here. Now see, an electric field was set up from this plate to this plate, which we have taken as E naught. Now another electric field is going to set up in an opposite direction in the dielectric slab. Now that will have this direction. Say E dash. Alright. So now you can see there are two electric fields. One is from positive charge plate of the capacitor to the negative charge plate of the capacitor, that we have taken as E naught. Inside the slab, certainly it will be small. We have set up, or it is being set up because of this polarity, an electric field in this direction. So a net electric field, or you can say because of this dielectric, electric field in this much space is reduced. by an amount E dash. So the net electric field inside the dielectric slab will be equal to, say, E, which will be equal to E naught minus E dash, which will be equal to E naught minus E dash. That means now we have got two values of electric fields. How? In the place where slab is not there, electric field is E naught. The distance or the space where electric field is E is T. How we had calculated the capacitance? Q is equal to CV. So C is equal to Q upon V. Let us consider if there was only air, how much was the capacitance? We already know. Epsilon naught A upon D. This you can take as, say, C naught. This is your equation number 1. Let us now consider the new capacitance, say C. How we are going to calculate? Q upon V. Now I'll find out the value of V as we had done in the parallel plate capacitor, exactly in the same manner. Now what is V? V, you already know that it is electric field into the distance. This we did yesterday. But now this expression is to be divided into two parts, because in distance D minus T, the electric field is E naught. And in the thickness T, the electric field is E, which is equal to E naught minus E dash. So this expression is to be divided into two parts now. So V is equals to E naught D minus T plus E into T. And what is this T? T is thickness of the dielectric slab which we have kept between the plates of the capacitor. Now this can be further written as, we'll do it as we had done it for deriving this expression. D minus T plus. Now we have already defined dielectric constant in terms of force. If you remember in the very first topic, which can further be written in terms of electric field, as electric field can be written in terms of force, and this will come out to be as E naught upon K. Take E naught common, we'll be left with D minus T plus T upon K. E naught can be written as sigma upon epsilon naught you can write over here as E naught is equals to sigma upon epsilon naught. Sigma can be further written as Q upon A as sigma is equals to Q upon A, epsilon naught will still be here. This is my V. Now this V now can be substituted in this formula. Substitute in equation number, say, 2. So this will be equal to C is equals to Q upon Q d minus T plus T upon K epsilon naught A. This is going to give me C is equals to epsilon naught A upon d minus T plus T upon K. So this is the capacitance of the capacitor if a slab of thickness T of dielectric constant say K is kept between the plates of the capacitor. Now from this expression we can go back to the similar expression that if the total space is filled with dielectric constant K, then the value will be C is equal to K epsilon naught A upon D. Now if suppose whole space between the plates is filled with dielectric of dielectric constant K, then T and D will be the same. Then T will become equals to D. When T will become equals to D, this will give you 0. This will give me D upon K. So what will be C equals to? K epsilon naught A upon D. So this value again we have got the same value. This expression you will use only when a small space is filled. Now from this expression and this expression you can see that C is equals to K C naught. Again we have obtained the similar expression. So in this way we can find out the effect of dielectric between the plates of the capacitor.